Hello, I'm Benedikt from TU Wien. I'm a PhD student on the Department of Compilers and Languages. I'm part of the Open WADL team, which was presented yesterday by my colleague Kevin Peer, and I will be talking about multidimensional match, transform and replace, or short MMTR. The whole thing will be about basically vectorization. It will be on a lower level than many of the talks we have heard on this conference. It's restricted to the LLVM IR. In LLVM, we already have, for single dimensions, powerful tools. For example, the loop vectorizer or the SLP vectorizer. The open problem is, what should we do with multidimensional optimized target implementations? For example, one could think of those as optimized library calls, for example, matrix multiplication in OpenBLAS, or the two-dimensional dot product, which we find, for example, in the Intel AMX extension. Normally, these are accessed by the programmer via explicit calls to those optimized target implementations. Be it the library call or the intrinsic call. But of course, this is not very portable and it's also error prone. So the goal of MMTR is to identify loops that can be replaced, transform them in such a way that it's possible to replace them, and then replace them by the optimized target implementation. We have observed that many of those optimized target implementations are semantically equivalent to a perfectly nested loop with a dense and rectangular iteration domain, a constant step size, a loop invariant iteration count, a small loop body with not too much control flow. These are pretty strong restrictions, and one could also see them as a list of things that we have still to improve on in the MMTR. These are suitable for analysis in the polyhedral model and also for pattern matching. MMTR is implemented as an extension to the Poly library, which is the polyhedral library, which is distributed with the LLVM distribution. And it's currently implemented in LLVM 19. So it works in the middle end of LLVM. There are two modes to specify dimensions. The parameterized mode, where the parameters, the dimension sizes are passed as parameters to the optimized target implementation. This is typically used for calls to the library functions, for example, in OpenBLAS, or fixed dimensions where the dimension sizes are restricted to a fixed value. This is typically seen in dedicated instructions which operate on, for example, vector or let's say matrix registers which have a fixed size. At this conference, I learned maybe the better terminology would be dynamic and static, but yeah, maybe we changed it later on. And also we have a TableGen backend, which allows us to give a short description of the target implementation, and from that we generate the matcher code. Just some short words about the polyhedral model for explanation. It's a compact representation of control flow and memory accesses. The one restriction is that all the indices to arrays and the control flow, so the branch conditions, have to be affine functions of loop invariant values, or let's say they are similar to linear functions, so not too complicated. All the parts that can be analyzed in the polyhedral model are called static control parts, so all short scopes. A polyhedral statement is just some piece of linear code. It's not exactly a basic block, but for this talk, I think it's sufficient to think of it as a basic block. A polyhedral statement instance is just one execution of such a basic block, so that all the iteration variables have one specific value. An instance set is the set of all these instances. An array access is defined as a mapping from a polyhedral statement instance to an array index. And the polyhedral schedule is similarly a mapping from a instance to a multidimensional point in time. And with these two mappings, in the polyhedral model, we use these two mappings to manipulate, for example, memory accesses, or can do some powerful loop transformations, for example, loop fission, loop fusion, strip mining, or tiling. What does MMTR need as an input? So for each optimized target implementation, MMTR needs an MPattern. This is the one that has to be matched. This consists of an instruction pattern, which basically matches the loop body of the loop in question. Then some information about the dimensions that have to be matched, all the memory accesses, and information about what we should put in place once there occurs a match. So this is the replacement block. In order to show how this all works, I will present a short example. This is just a typical implementation of a matrix-matrix multiplication. So we have two input matrices that are multiplied and written into one output matrix. Note that there is also a initialization block. This will become important a little bit later on. But apart from that, the loop body is pretty straightforward, what one would expect with the multiplication and the accumulation. So how can we specify this MPattern for MMTR in TableGen? Let's say we have a optimized target implementation for a vector matrix multiplication. So we have to first specify the instruction pattern, which is just a tree pattern. This is pretty straightforward. Also with the multiplication and with the addition, with the accumulation. This maps directly to the pattern match facilities that are available in LLVM. Additionally, we have to specify the accesses. So in our case, we have 3 read axes and 1 write axis. The most interesting one of those is the one to the array B, which is the matrix axis. So it's the axis to the 2D vector. So we 2D matrix. And then we put everything together. So first we have the instruction pattern. So the next thing is something new. It's the information about the dimensions. So in our example, we have a fixed dimensions with the inner dimension, with the outer dimension of size 6 and an inner dimension of size 4. Then we list all our accesses we have defined here. And in the end, we just specify the call to the optimized target implementations, which is just a function name and all the parameters that have to be passed to this optimized implementation. How does MMTR go about matching these things? It starts with matching the loop body. So it takes its instruction pattern and checks whether all the instructions in the loop body are equivalent to this pattern. And it also captures values that may be needed in later parts of the computation. For example, it could capture the pointer values that are then passed as parameters. Then it checks the size and the shape of the instance set. In our case, this is yet restricted to a rectangular shape. And then it for each memory access, it checks whether it maps to the specified patterns. So for this, in our case, it has to project to 2 dimensions, so to the innermost 2 dimensions, which means that this I0 just goes away, and what remains is this. And as we can see, this more or less looks like the one that we are trying to match modulo renaming. And in the end, it gets some information about the stride size, which is important to access the matrix. And this is also done by available functionality in Poly, which is the array info. So this would be the matching part, but we also have to do some transformations. There was this block where the initialization to 0 happened. So this is something that we cannot match or cannot replace with the optimized target implementation. So we have to move it out of the way. This we do by manipulating manipulating the schedule tree of Poly, which allows us to move this basic block out of the way by using loop fission. So it went from this inner part just out of the looping question. And since we have a fixed dimension setup, we also have to do loop tiling. So again, we use Poly's functionality for loop tiling. And this provides us with the prologue and the epilogue. And what remains in the center is just a nested loop that is equivalent to our MPattern, to our optimized target implementation. These transformations are in general not safe, so we have to check the validity of the schedule, whether it's still valid. Then, if that's the case, we set the replacement mark, and during the emission phase of Poly, we just take out the nested loop, and replace it with the call to the optimized target implementation, providing the captured arguments. We did an evaluation of this, with the target implementation being OpenBLAS. For this, we provided 4 patterns. One matrix multiplication, which is the 3-dimensional pattern. One 2-dimensional pattern, which is the vector matrix pattern, just like the one that we have seen in the example, and 2 1-dimensional patterns, the dot product and the vector addition. And in Polybench, we managed to get 7 out of the 30 benchmarks out of the suite with matches. We have a very nice speed up for the 3-dimensional cases, and also a good speed up in the 2-dimensional cases. And the 1-dimensional cases about the same as the normal LLVM vectorizer. The good results are mostly thanks to OpenBLAS and the fact that these benchmarks just are very well suited for the OpenBLAS implementation. In addition to that, we checked the visual wake words benchmark from the MLPath Tiny benchmark suite. We used TVM Micro to generate C code from the model file. And in this, we managed to get 4 matches in hot functions, which reduced the runtime by the runtime of the inference by 66%. Future work will be generalizing access patterns and generalizing the size of the iteration domain, or the shape of the iteration domain. And also, probably, we have to provide a better cost model. The whole prototype is available at our OpenVadel project. Yes. And this was my talk about MMTR. Thank you.
We probably have time for one question. Any question?
Thanks for your talk. Michael Kruse here. I'm current co-owner of Poly. Poly already has like a matrix multiplication detection and optimization. Would have this a potential to replace that, to be detect arbitrary patterns?
I think the Poly matrix detection is mainly focused on optimizing memory accesses. So it has a little bit of a different goal in mind. I'm not quite sure whether it can replace it, but I would have to look into it. Whether there's certainly some overlap in the functionality, but I cannot tell whether it's it's replaceable by our approach.
So is there opportunity for like a rewriting or match process be done by like LLM AI process or like a Colama or some models? Or?
You're talking about MLIR passes?
I mean the match and rewriting is possible done by AI use like
okay.
LLM model or Colama. Or
I don't know. I have not thought about this.
Okay.
Maybe it's possible, but so far it's everything done by hand, basically.
Okay. Thank you. Thank you very much.
I have one question.
Oh.